let's finish 4.5. 4.5 is all about these logarithmic and exponential equations and solving them. So last time we solved a log equation where we had to compact it, and the idea is basically if you're solving a log equation, so I'm going to call this example 1 today, that at some point you're going to be raising it to some power to cancel out the log. So for instance, if I say ln of x is equal to 8, there's a log equation, and then let's say log base 2 of 25 minus x is equal to 3. Okay, so the idea is when you're solving a log equation, first get anything that's attached to the log operation. So looking at part A, anything that's attached to it, get it off, basically. If there's anything added or subtracted to the outside of the log, move it over. If there's anything multiplied or divided onto the log, scoot it over. In this case, nothing is there. We just have the log. It's all by itself. So what I do to cancel out the log is I stick an exponential in there to cancel out the log, because that's what exponential and logs are, inverse functions of one another. So I can raise both sides with a base of e, like this, ye, because, and it needs to happen to both sides. I'm setting e as the base. And why is it e? Because e is the base of the natural log. Remember, this is a special log that has a base of e. So that's why I'm using specifically the number e here. You'll see in this other problem, I'll use a different base because this is a different kind of log. Now what happens here is on the left side, they cancel each other out. They're inverse operations of one another. So it just pops out the x, just pops out x, and then that's it, because there's nothing else to do on the right side. So the exact answer is this, and then if I wanted an approximate answer. So the exact answer has these infinitely many digits stuffed into this little symbol e raised to the 8th. But if I wanted to get an idea of like how big this number actually is, I would go to the calculator and type e raised to the 8th. And I'm getting approximately 2,981. So there's an approximate answer. All right. Part B, a similar thing. I'm looking at this log equation and I'm saying, is there anything happening outside of the log? Now I know there's stuff happening inside the log, but that's okay. That's okay. Is there anything added, subtracted, multiplied, or divided on the outside of the log? And the answer is no. So that means I can go straight to the step, just like this previous problem, where I introduce an exponential operation. And this time, instead of picking e as my base, I'm going to pick 2 as my base to match the log. So I'm going to say 2 raised to log base 2 of 25. Just basically this whole thing gets stuffed up in there. And then same thing on the other side, and make sure you don't accidentally say 3 squared, right? It's 2 raised to the 3rd. These two pieces of the original equation become the exponents. They get pushed up into the exponent position. On the left side, the exponential base 2 here and the log base 2 cancel each other, just popping out the input of the log. So I'm getting 25 minus x is equal to 2 cubed. There, 2 cubed is 8. I can go ahead and say that. 25 minus x is 8. And now I solve for x. So the last steps, once you get rid of the log, should be like relatively easy. It's just a linear equation. You can solve it however you want to, add the x, subtract the 8, or I'll subtract 25 from both sides. So I have negative x is equal to negative 17. So then x must be positive 17. And then, of course, when you get an answer like that, you don't need to go get an approximate answer, because this is fine, right? There's nothing to plug into the calculator. It's just a whole number. So this would be the entire answer there. Okay. So that's just more of that technique that we really used last time about solving log equations by raising each side, pushing the pieces from the original equation up into an exponent position and using the base to match the log. Okay, let's try another one that the book gives as a separate example. To be honest, it's pretty much the same thing though. But I'll call it a separate example here. Example 2. We're going to solve 4 plus 3 times log of 2x is equal to 16. Okay, so last time I said that the first thing we need to do is get anything that's attached to the outside of the log off of the log. So that's exactly what we do have to do here. So Kimberly, what would we do? What operations should we do?
I believe you subtract the 4.
And then divide by 3, right?
Right.
In that order, yeah. So we'll subtract 4, so I'll write these as separate steps. 3, 12, there we go, subtracting 4. And then dividing by 3, log of 2x is equal to 4. Okay. And now we're right back to where we were basically with the previous example. So always get everything off of the log first. What would I raise this to, or what would the base of my exponential be?
10.
Yep, because it's a common log. So it would be 10 raised to log 2x equals 10 raised to the 4th. Good. Okay, and the reason it's 10 is because whenever we see log without a base written, we know its base is technically 10. It's the so-called common logarithm. Gets its own notation with its own special base. 10, this 10 exponential and the log cancel out, leaving us with just the input. And by the way, 10 to the 4th is 10 times itself 4 times. In other words, 10,000. And then dividing by 2. So one thing to remember is that this step, when the exponential and the log cancel, doesn't always just give you x, right? It gives you whatever was in the input. So at the end, you might still have to do a couple steps to solve for x. But usually at that point, those steps are very easy because usually they're just like a linear equation, meaning no exponents or anything to worry about. Just some either addition, subtraction, multiplication, or division will get you to the solution. Okay. All right, one more example, similar to one that we did last time, but it's going to be a little different. Well, why is it different? It's going to be, so I know I'm kind of flying through these, but I want to make sure I have time to talk about 4.6 today too. Plus, these are kind of like the same techniques that we've already looked at, just kind of like flexing those techniques a little bit. So let's solve the equation. Okay, now we're going to have the thing where we have 2 separate logs. So plus, these things are separated by a sum. It's equal to 1. We want to solve it algebraically, like we've been doing. That means like with symbols and operations and such, and graphically. So we worked a problem like this in the earlier in the section. I think it was example 3 or 4 for exponential equations, where you could solve the exponential equation graphically, and we'll see you can do that with the log equation too, in a very similar way. So first thing we're going to do though is solve it algebraically, which means just by the normal method, well, normal meaning you write down the equation and you try to solve for x using algebra. So log of x plus 2 plus log of x minus 1 is equal to 1. So when you've got two or more logs separated by addition or subtraction, what you've got to do is compact them into one log. And we have a law for this that says if you've got the sum outside, two logs, the sum outside, that's the same as having the product of their inputs inside. So in other words, multiplying x plus 2 times x minus 1 inside. Okay, so this is law, I believe, law 1. Yeah, law 1 from 4.4, which is also, it's on the formula sheet that you're going to get on the final exam as well. And the formula is not hard, right? It's not hard to remember, but knowing when to use it, right? That's the tricky part. And knowing when to use, how do you know when to use it? Well, when you're trying to solve a log equation, the idea is that you get to this point where you have one log with nothing attached to it over here, no addition, subtraction, multiplication, division, equals one thing over here. And then you can solve it just by raising both sides with the right exponential base. Since this is a common logarithm, I can take 10 to be my base, because the base of the common log is 10, just like the one we worked a second ago. So here, it's not 1 raised to the 10, it's 10 raised to the 1, right? The 10 gets shoved up under both of these. 10 and the log cancel out here. 10 raised to this log base 10, they cancel out, just pops out this input. So I'm going to have this x plus 2 times x minus 1 is equal to 10 to the first is just 10. And now from here, I actually said a second ago that the last few steps will always be easier because they'll be linear. Well, this one's not, right? It's not going to be linear. It's going to be quadratic, so you still have work to do to solve for x because you have a quadratic equation now, but it is kind of a nice quadratic equation. And we'll see that when we multiply this out. So even though it's already nicely factored here, we can't do the thing where we split it and set them each equal to 10, because that only works when you have a 0 over here. So in other words, what you have to do is expand this out, get the 10 put in there with the quadratic equation, and then refactor it. So what we have to do is expand this. So I'll say x squared minus x plus 2x minus 2, just multiplying, distribution here. And then combining some like terms, x squared plus x minus 2 is equal to 10, just combining these like terms. Negative 1 plus 2 is 1 right there. Now I need to get the 10 involved. So remember, whenever you're solving a quadratic equation, you need to have a 0 right here. That's why I have to expand this and get the 10 scooted across. And now what I do is I hope that this can refactor really nicely. Otherwise, I'll have to go use the quadratic formula. So I could use the quadratic formula at this point. In fact, I might just do it anyways, just real quick, just to remind you how that goes. But this will actually, oh wait, does this factor nicely? Oh, well, it would if I did my arithmetic right. Look at that. That's not right. I added 10 to both sides. I should subtract 10. X squared plus x minus 12, right? Subtracting 10 to both sides. That's what I get for talking too much while I'm trying to write. So I look at this and I try to decide, okay, can this factor nicely? I hope so. That way I don't have to use the quadratic formula. And it does factor nicely because I'm thinking of two numbers that multiply to give negative 12, that add to give positive 1. So I know that that should be positive 4 and negative 3. And then I can split these two factors, set them each equal to 0. Again, can only split the factors when it's equal to 0. Couldn't do that all the way back here when it was equal to 10. Cover up that mistake there. Okay, so I'm getting two solutions here. X is negative 4 and x is 3. Okay, now there's still more to be said here. Anytime you get negative solutions, or sorry, more than one solution, multiple solutions is what I meant to say. Let me write this down. Anytime we get multiple solutions to log equations, to logarithmic equations, we should check the solutions. Why? We didn't have to do that for other kinds of equations, really. I mean, checking your work's always good, you know, but it wasn't necessary. It's just a nice little extra thing to make sure you did your algebra right. So why do we have to check the solutions for logs? Because logs are one of the first functions we're dealing with a whole lot where the domain is pretty restricted, because the log domains, the log, how should I say? Operation, the log operation cannot take in, what was the domain of logs? It can't be 0. It can be right up to 0 and higher, but nothing below 0 or including 0. Cannot take in 0 or any negatives. Now, that doesn't just mean that we immediately discount our negative solution here, because it depends on what was going on in the input of the original log, in the original problem. So what I'm going to do is rewrite it right here and say log of x plus 2 plus log of x minus 1 is equal to 1. Let's check x equals 3. Let's check this one. So literally plug in 3. Log of 3 plus 2 plus log of, so I'm not so much checking to make sure my answer is correct here. I'm more so checking to make sure I don't get any domain error inside the log. Like, I don't want to see a 0 or any negatives in here once I do this little arithmetic. Now, as a byproduct, I'm also going to be able to just go ahead and check if my answer is right, which is nice. So first of all, there's no domain errors, right? So this is fine, probably as a solution, that it doesn't break the equation. Okay, but let me just finish it and see if it's actually right. Well, how do I do this, right? Well, I use the law 1 again that says if I've got a sum outside, that's a product inside. So log of 5 times 2 is 10, right? Not log of 7. I don't add the inputs, I multiply the inputs. And then is this true? Well, this is a log base 10. So what this asks me is 10 raised to what power is equal to 10? That's what this log asks. And it's saying equals 1. Is that true? Yes, because 10 raised to the first power is 10. So this is true. Well, there we go. Okay, what about the other solution? Let me slow down a little bit. Okay, so now I'm going to check the other solution, and I'll just temporarily cover this up here. X equals negative 4. I'm going to say the same thing. Log of x plus 2 plus log of x minus 1 is equal to 1. I'm going to plug it in. So remember what I'm looking for here. I'm looking for anything where it gives me negative values or 0 inside the log. That breaks the log. And look, you can tell they're both going to be negative. So we get domain errors. So x equals negative 4 is not a solution. You can't have negatives inside of a log. And clearly negative 4 plus 2, that's going to be negative. They're both broken, right? Negative 4 minus 1, that's going to be a negative 5. So it doesn't always mean, though, that if you get a negative x value here, that it's, because what if it was x plus 7? the -4 plus 7 would still be positive, right? So don't just discount an answer just because it's negative. It really depends on what's going on inside the input, what's happening to x inside the input. Okay, but so the thing is, anytime you get two solutions to a log equation, or two or more really, anytime you get multiple solutions to a log equation, you got to check each one to watch out for domain errors like this. Why are there domain errors, by the way? Where do they come up? Well, it's just in the way well, it's kind of some subtlety going on, but basically when you're solving an equation and you introduce a quadratic equation as part of your solution, which is what happened back here, you are always introducing the potential for extraneous non-solutions to end up cropping up. And there's something to be said there, but just for now, what I want you to know is just, if you do end up in this situation, just keep this in mind, what I wrote in black there. All right, I'm not quite done with this. I wanted to backtrack a little bit. Well, I'm done with the algebraic solving. I'm going to graph it for you too and show you how to graph the answer. But I also wanted to do one more quick little thing, which is to remind you how you can solve this thing via the quadratic formula if you don't want to factor it to find the two x solutions. X is equal to -b plus or minus b squared minus 4ac all over 2a. In this form here, a is 1. That's the coefficient up here. So a is equal to 1. B is also equal to 1, right? That's the second the coefficient right here in the middle on the linear term. And C is -12. If I plug those in, -1 plus or minus square root of 1 squared minus 4 times 1 times -12 all over 2 times 1. X is equal to -1 plus or minus 1 plus 48, right? Oh, the negatives cancel in there. 4 times 12 is 48, and the double negative makes it positive, all over 2. I'm going to run out of room to do all this. You may have to finish the simplifying on your own here. Anyways, 1 plus 40, let me skip some steps here. 1 plus 48 is 49. We know the square root of 49, that's a nice clean square number, so square root of 49 is 7. So -1 plus or minus 7 all over 2, and then you would split these into -1 plus 7 over 2, or -1 minus 7 over 2, and these would simplify. This would end up being 3, because this would be 6 over 2, and then this would be -8 over 2. So you get the two solutions, -4 or 3. You still have to go check them, right? That's an additional step for the log equation. I just wanted to remind you here in blue how to run the quadratic equation. I mean, quadratic formula, sorry. Quadratic formula for a quadratic equation. All right, let's solve it graphically. So let me go to Desmos and I'll share my screen. So we actually solved an exponential equation graphically last time, and the way we did that is we took each side of the equation and set it equal to y. So I'm going to do that here. I'm going to say y equals log of x plus 2 plus log of x minus 1, and that's it. And then the other equation, or the other side rather, was just a 1, like literally the number 1. So I say y equals 1. And what I'm looking for here is where they intersect. What is the x value where they intersect? Well, it's a 3. It's a 3. That 3 is what we got as our solution, right? The graphical method is much easier, right? Because the computer does all the work. It also does not introduce any extraneous solutions. Remember, our algebraic solution gave us x equals -4 as a solution, like somehow all the way back here at -4. And that's just a byproduct of the way we solve it algebraically. So you have to check solutions. The graphical way does not introduce any extraneous solutions. So, in a lot of ways it's superior. One of the ways that graphical solving is not superior, well, the most obvious reason, I guess, is that you don't always have the technology. Another reason is that if you get a irrational solution, like a square root, like we got kind of lucky, we got a whole number 3, right? But what if it was like square root of 3? Well, then the graphing calculator, at least Desmos, would not tell us that it was square root of 3. It would give us the decimal approximation of that, which is fine. It's still an approximate solution, but we wouldn't know the exact answer. If we wanted the exact answer, if it's a really ugly, irrational answer, but we wanted to be able to know exactly what it was without a decimal approximation, we would still have to do it by hand. Okay. I use the graphical method for solving equations a lot because it's just so much easier. Even if I'm going to give you guys a question, back when I made my own exams, didn't use WebAssign for them and had to do my own homework or whatever, if I made an equation, I would go plug it into Desmos just to see what the solution is and say, oh, that's reasonable, or maybe it's not reasonable. Okay, so let's see, where else do we want to go here? It's 12, no, it's 1 o'clock, okay. Formula for... Oh, hey, Taylor, what is your major? I'm just curious. It matters for what I want to do in section 4.6.
My major, I'm changing it. So it used to be nursing, but it's exercise science and wellness now.
Okay. So the reason I'm asking is section 4.6 deals with, basically they throw a whole bunch of applications at us, like real world problems in biology, physics, and chemistry. And I was already leaning towards biology, and Kimberly's major is in really biology and chemistry, but I think mainly biology, and yours would fall into biology as well. So yeah, I'm going to stick with that then. Let me read this. I want to read this compound interest thing, see if I want to do this example. Let me also look at the problems I'm giving you guys. Where's number 49? No, that's just a... Sure, let's do this one. So example 4. So we learned about the continuously compounded interest formula in section 4.2, I think. And I probably posed a question like, how do we solve for time in an equation like that? And let's go ahead and run one as an example. So a sum of $1,000 is invested. And the reason I posed a question like that is because it involves logarithms, right? So here's an official example of that kind of problem. At an interest rate, all right, here we go. Interest rate of 4% per year. Find the time required for the amount to grow to $4,000 if interest is compounded continuously. So there's actually a whole lot to be said about savings accounts. We only really scratched the surface in this class. In my discrete math class or finite math class, oh, by the way, the formula for continuously compound interest is this one. So just so you know, what would probably be more likely for someone like a college age student or even me, right? We don't have like giant lump sums of money sitting around that we can invest by just plopping it into an account and letting it gain interest. More than likely, the way we save money is through something called an annuity savings plan, which means that you make a plan with your bank where you drop like $50 or $100 or whatever per month from your paycheck into a savings account. And then it gains interest over time as you keep stacking money into it. That's called an annuity savings plan. The reason that these compound interest things come up, even though they're like less likely for us to be worried about them, because like I said, we don't have tons of money that we can just plop into an account all at once. The reason they come up is the formulas are just really nice and clean, and they're great examples of exponential functions. But just so you know, if you ever wanted to do calculations, if you're ever interested in getting an annuity savings plan, the math, if you can do this math, the math for the annuity savings plan would be well within your grasp to do. Okay, so here we go. We want to know, find the time required. So we're solving for t. So t is up in the exponent position. To me, that's telling me that we're going to have to get a log involved. For the amount to grow to $4,000. Okay, and by the way, interest compounded continuously. That's why I'm using the continuously compounded interest formula. Because recall, there's another formula where it's not compounded continuously. It's like p times 1 plus r over n raised to the nt, different formula. So in this case, my initial amount is 1,000. That's the value p. The e is a number, so I don't plug anything in for that, right? That's going to go into the calculator. or well, you don't plug anything from the problem in for e. R is 4%, so that's going to be 0.04. And I'll say in parentheses and then times t. Remember, percents need to be turned into decimals, so divide 4% by 100 to get it as a decimal. And A is going to be the amount in the account that is the goal, which is 4,000. So now what I'm going to do is I'm going to flip this thing around, and just because we like to have the thing that we're solving for on the left side. So all I'm doing here is flipping it around. And just like with logs, whenever you're solving an exponential equation, you want to get anything that's attached to the outside of it away from it first. So the first thing I'm going to do is divide by 1,000, because 1,000 is attached to this via multiplication. So I want to undo that by dividing by 1,000, and 4,000 divided by 1,000 is going to clean up very nicely to just 4. Now what I need to do, now that everything's gone from the outside of the exponential function, there's just stuff buried up in its input, which is fine. I'm going to take a log on both sides to cancel out the exponential. Specifically, I'm going to take a natural log because that's the one that has the same base. I want to match the base of my exponential operation with the base of my log operation. And the log that has a base of e is this special natural log. So I take natural log on both sides. On both sides. Can't forget to do it on that side as well. Left-hand side cleans up because the natural log and the e operation, or the exponential operation here, cancel, just leaving me with the input up here, which is 0.04 times t. So I'll just write it as 0.04 t. Maybe I can say times. There we go. Equals ln of 4, which this is going to be some crazy irrational number, but for now I'm going to leave it in this compact form. And then finally, to solve for t, I'll divide by 0.04 on both sides. So here is my exact solution. This is my exact solution. But, you know, in the real world, you want more than that. You want a, I'm going to come over here and get approximate. You want to know, like, how many years is this, right? If you ask me how many years will it take, and I say, oh, natural log of 4 over 0.04, that's not an answer, right? That's a math class answer, an exact answer. But what you really want is an approximate number of years, something that's easier to look at. So ln of 4 divided by 0.04 is 34.657. So I'll just say, if I round to the 10th place, 34.7 years. So roughly 35 years is how long it would take. So that's just one. This is an example, an application of exponential or log equations in finances. Okay. So I'm going to put it in the chat, but I'll just tell y'all since you're here. For 4.5, the problems to add for you to mark for review are going to be 3 and 49. So basically just a nice little exponential equation. It's more like the very first example I worked from 4.5, or first or second example. And then 49 is a log equation. So similar to, I think the very last problem I worked, it's example 7 in the text. Where is it? There it is, yeah. Hang on. Is that what I meant? One second, I'm not sure if that's the one I wanted to pick. I wrote 49, but dang it. Sorry, give me 1 second. 10. No, that's not what I wanted. Dang, I'm gonna have to go change the exam. 63 is actually what I want to say. 63. Change that here. And need to make sure I put the right problem on the exam too. 63 is like the one I worked today. Example 3. It's like that, example 3. And I want you to be able to solve it algebraically, not graphically, because asking you to solve it graphically isn't really asking you to do anything at all. So I want you to be able to solve it algebraically. Okay. Now let's get into 4.6, which is basically just a whole bunch of applications. It's called modeling. Modeling means like putting math to real life problems with exponential functions. But also, surely there's going to be some log function. Well, anytime you're dealing with exponential functions, there's going to be log functions too. They'll pop up. Oof. Okay, so give me 1 minute to look at. So now that I know that I'm leaning more towards the biology ones, I'm actually going to be changing the formula sheet to reflect that, because if you have looked at the formula sheet that I put in Canvas that you'll have access to in the final exam, you'll see right here I've got exponential growth of a population, so I'm going to work one of those. And I've also got a radioactive decay model, which is super interesting, but it's like chemistry, and so we won't. I'll replace this one with the exponential growth for doubling time for a population. In other words, like if you've got bacteria that grows by like splitting or whatever. So I'll be changing that. Okay. Let me get back to Teams. Okay. So I think I opened this whole chapter with an example about exponential growth. Like if you've got some little bacteria and the way it reproduces is it splits itself, and then those two pieces split themselves, and that's a great example of a exponential growth, right? So when When we have that kind of exponential growth, we have this formula. So let me write out the pieces to this formula. If the initial size of the population is n sub 0. So if you've never seen this notation before, n is just like number of things, right? N is just a variable. And when you see subscript 0, that, and it's sometimes read as n, not like that, not NOT, but NAUGHT, and not. You may have seen that if you've taken like a physics course before, like when you're talking about initial and final velocity, sometimes people will call initial velocity V naught. Anyways, okay. And the doubling time is A. Then the size of the population at time t is, so it's a function of time, number of things in the population dependent on time. So there's our function notation. Independent variable is time. The thing that depends on that, the dependent variable, is n, the number of things. First of all, it's going to be that initial population, and then times an exponential function of base 2. Why is it base 2? Because we're talking about doubling time. And then it's going to be raised to the t divided by a, the time it takes for it to double. And where a and t are measured in the same time units. So they both need to be in the same units. Unit being like hours, minutes, seconds, etc. The same time units. Okay. So the T over A thing is just saying, like, well, it's going to make the most sense if we do an example. Let's run an example so we can see this formula at work here. So let's say example 1 here. A certain bacteria population doubles every 3 hours. So that's the doubling. That's the doubling time there. Doubles every 3 hours. Initially, there are 1,000 bacteria in a colony. Part A says find a model. A model is like a function or an equation like this for the bacteria population after T hours. And part B says how many. So once we have the model, we're asked to use it here. How many bacteria are in the colony after 15 hours? Part C is going to say, it's going to ask us for time. Yep. After how many hours will the bacteria count reach 100,000? Okay. So we're going to use this. How do I know I should use this generic model here that I've written up here? This N of t thing. Well, because this is for specifically for a population that is doubling. Like over every period of time, whatever it may be, in this case 3 hours, it doubles, right? That's not how every population grows, but I guess I don't know anything about biology, but I guess that's how bacteria grows because of the way it reproduces. I don't know. But apparently some populations do follow this model, and in particular this one does. It doubles every 3 hours. So I know I'm going to use this. Now I need to decide what each piece should be. So part A should look like N of t. First of all, that's just the function notation telling me number of things, number of bacterias at time t is equal to N naught. That's the initial population. There we go. Initial population is 1,000, and then times 2. 2 is just part of the formula. T is part of the formula. And over A, where I need to figure out what A should be, I do have to plug something in for A. A is supposed to be the doubling time. How long does it take to double? In this case, 3 hours. So this is 3. That's it. That's all you need. You need to figure out the initial and then doubling time. Okay, that's it for part A. You've built a model modeling bacteria population given initial population and time it takes for the population to double. And remember order of operations, right? This is not the same as 2,000, right? You can't do 1,000 times 2 raised to the 2/3, right? This is an exponential function times some constant up front. Okay, part B says to, what does it say? How many bacteria, so it's asking for N, are in the colony after 15 hours. So the most appropriate way to write this is N of 15. I'm plugging in 15 into my new function here, times 2 raised to the 15 over 3. So I plugged 15 in for T. So I'll say N of 15. I'm just carrying this over. So I need to raise 2 to the 15 over 3. 2 raised to, and of course you probably already know 15 over 3 is 5, but I'll just plug the whole thing in there in parentheses. There's that part first, and then times 1,000 is 32,000. So do the 2 raised to the 15/3 and then times 1,000. Order of operations, right? Exponents and then multiplication. So that part's easy enough, literally just plugging into the function. Part C is a little bit more involved because it says after how many hours. So how many hours tells me I'm asking, they are asking for T. They're asking for T. Will the bacteria count reach 100,000? So now what they're telling me is in this formula, N of T now is equal to 100,000. So I literally replace N of T with 100,000. And then I plug in, and then I, carry the formula over with T still being unknown, right? Because that's what I'm asked to solve for. So now I have an exponential equation, right? Just like 4.5, section 4.5, I need to solve this. The first thing I do is get anything attached to it away from it. So I'll divide by 1,000 on both sides. So 100,000 divided by 1,000 will end up being 100. So again, from this formula, for part C, from this formula, I'm replacing the output of the function with 100,000 because they gave me that output. And I'm solving for the input. In order to solve for the input, I'm going to have to do some algebra to get from this to T equals a number. I'm going to have to do some algebra, introduce a log function too. First step I did was divide off this 1,000 that was attached to the outside of the exponential operation. And 100,000 divided by 1,000 is 100. Okay, now I'm going to come back over here. Now, let me just flip this around because we like to have that thing that we're trying to solve for on the left-hand side. Now I'm going to introduce a log. I'm going to take a log on both sides. And I need it to match the base of my exponential operation. So I'm going to take a log base 2 on both sides. Not worry about the right side yet, though there's something to say there. Log base 2 of 2 raised to the t over 3, that these cancel each other and it just pops out the t over 3. So I'll write it like this. T over 3 is equal to log base 2 of 100. Let me scoot this up. Still trying to solve for time. Oops. There we go. Before I multiply by 3 on both sides, because you know that's going to be the last step to solve for t, let me recall my change of base formula. Because whenever I've got a log that's not a common log or a natural log, I need to use the change of base formula to rewrite it so that it can be plugged into the calculator. So recall that that's just the same as writing common log of 100. In other words, just drop the base thing, and then over common log of 2. Just like that, you put the common log of the base in there. So that's coming from the change of base formula. Finally, multiply by 3 on both sides, so 3 times this fraction. That's my exact answer, but if you really want to know how many hours will it take, then you're going to plug it into the calculator and get an approximate solution. 3 times common log of 100, and I'll hit equals, and that's 6, and then divided by log of 2, common log of 2, and I'm getting approximately 19.9 hours. So, you know, basically 20 hours before it reaches 100,000. Okay, so next time we will do another population problem, and then we'll look at, well, no, we're going to do like 2 or 3 more population problems, and that'll be it for 4.6. That'll be it for the all the new material. So Monday we'll finish 4.6, and then Wednesday and Friday we'll review. Okay, you guys are good to go. You can stick around if you have any questions.